Today we're going to look at the properties of tangents on page 11 within a circle. So recall that a line that intersects a circle in exactly one point is the point of tangency. So if we take a look at that circle that you see on top there, you have that a tangent line would be a line that passes through the circle at that single point. And clean that up a little bit here. So this point right here, we would call, let's call that A. Point A is your point of tangency. So if you take a look at the theorem below that, you see if I were to flip that sideways, that sometimes people call this the ice cream cone theorem. So if you picture that this is your scoop of ice cream there, and then that's your cone. And so what we observe is that if you have two lines with a common point on the outside, S, and you connect the center to the point of tangency on each side, that radius is perpendicular to the line of tangency. So perpendicular here as well as here. If you actually divide and connect Q to S, you can see that you form actually two triangles, and we'll speak roughly about what we observe here. But what you now have is two right triangles. If you think back to earlier in the course, we had talked about right triangle theorems that prove two triangles are congruent, one of which was HL theorem, where H stood for hypotenuse. So reflexive property, we have that the hypotenuse is shared, so those are congruent to each other. We know that this and these two segments are the radii, so they must be congruent to each other. So by HL theorem, you have that triangle QPS is congruent to triangle QRS. And so a whole slew of information follows. So if you recall, Cpctc means corresponding parts of congruent triangles are congruent. So certain things emerge, like the fact that this angle right here and this angle are congruent by Cpctc. You have that this side of the triangle is congruent to this side of the triangle by Cpctc. So we'll say PS is congruent to RS. We'll say that angle PSQ is congruent to angle RSQ by Cpctc. So after that, you'll have a series of questions that ask you about different values that are missing based off of those observations that you see there. Okay, one thing that I'm going to note is that if you do have a line that is tangent to the radius, what it forms is right angles, and we see that up above in that triangle right there. It's the same, and I'll highlight it right here. So this area is really the same thing as this area right here. And so I'll just summarize it, what that theorem says though. But if you have if OR is perpendicular to L, then line L is tangent to circle O at point P. Sorry, point R. So let's go ahead and look at some problems that might show up on these on the tangent properties in circles. So you have AC is and AB are tangent segments. AB is equal to 12, which is marked here. AO is equal to 13, and BAO, angle BAO, is 23 degrees. So if you connect O to C as well, you get the two triangles that we discussed on the ice cream cone theorem. And certain things emerge, like the fact that the length of r is this or this, and we can find that by Pythagorean theorem. But if you do the hypotenuse squared is equal to the leg squared, then you can solve for r and find that it's equal to 5, or know that 5, 12, 13 is a Pythagorean triple. So the r value is 5. AC in the picture is the same thing as AB, or is incongruent to AB. So AC is 12. And angle CAO is a corresponding part to BAO, so it also must be 23 degrees. If you can go ahead and scroll down here, and I'm going to have you guys finish these problems off as part of your homework assignment. But question number 2. If you know that OC is equal to 3 rad 6, so this segment right here is 3 rad 6, and BC is equal to 6, we can use the idea of Pythagorean theorem to then find the length of OB. For the problems that ask for AB, which is the diameter, you just make sure you double. So in this example, we have that the hypotenuse is 3 rad 6, and we're going to square that. Set it equal to the leg squared, the sum of the legs squared, so 6 squared. And we don't know what OB is equal to, so we're going to call that x squared. To square 3 squared of 6, you're going to square 3 first, you get 9. Square the square root of 6 and you get 6, equals 36 plus x squared. So 9 times 6, 54, equals 36 plus x squared. Subtract 36 on both sides, and we get 18 equals x squared. Solve for x by taking the square root of both sides. Simplify the square root by taking out 3. Square root of 9 is 3. 3 rad 2 is the length of